Welcome to another unit in business mathematics. This time I'm going to talk about the so-called Gauss algorithm, which is a procedure we can use to solve linear systems of equations. If we start, well, basically, first off, we have to discuss what is a linear system of equations. And that's more or less a way of writing a set of linear equations as we have them here, meaning each variable x is to the power of 1 and they only have a coefficient which could be a constant, so parameter or a number. And on the right hand side we have some absolutes, being them again parameters or numbers. So it's basically what we know as linear equations, with the only difference that we have in this case more than one variable. So we could, as in this example, have like x1 to xn, so have n different variables, and we have a set in this case of m different equations. And if we want to solve these linear systems of equations, there are actually quite a few possibilities, quite a few procedures we can use. First off, however, let's make this rather unwieldy notation a bit easier. And the easiest way to actually write down a linear system of equation is the so-called matrix vector notation. So in other words, we have a notation like this, matrix A, which contains all the coefficients from the left-hand side, so the A11, A12, A21, and so forth, multiplied with a vector x, which contains all the variables we are looking for from x1 to xn. And we have the right-hand side vector, which contains all the values on the right side, which is the b1 to bm. So that's actually here this part. So we just summarize this, because then it makes the working and the solving of these equations or systems of equations much easier. And we don't have to write down this much all the time. Okay, so we know how to easily write this down. How to perhaps solve something? Well, let's consider first this system of equations. If we want to rewrite this in matrix vector notation, this would look as follows. We have, and I can show this here, this 2, which is here, this 2, which is here, the 1 in front here, the -1 in front, which is here. If at one point you were to be missing one of the variables, so if this would only be x1, then we would have 1 here, and well, there would still be an x2, you wouldn't see this because the coefficient would be 0. So for every variable you're missing, you're putting a 0 here in the matrix. So that's the matrix on the left, and the vector on the right, that's 2 and 1. The two variables we're looking for, x1, x2, are given here. So that's the matrix vector notation of this system of equations. And for solving it, one way would be we can calculate the inverse matrix to the matrix A, so this matrix here on the left, and then simply, once we have this, multiply this with the vector on the right. So that's the idea here. If we do this, we actually get the result to the system of equations. There's only one big problem. While this is relatively straightforward if you understand how you can calculate inverse matrices, mathematically speaking, it's a really inefficient way to solve linear systems of equations. That's why in practice you would never go and determine the inverse matrix and then use it to solve only a system of equations. If you were to do this, however, well, here the solution would be 1, 0. Okay, so this is not the ideal way to go, so what can we do instead? The alternative would be the Gauss algorithm. Well, usually also use the Gauss algorithm to directly get the inverse, so it's a good idea to learn this here. The Gauss algorithm actually means I have my matrix here, system of equations here, and I'm focusing mainly on this matrix. Because what I want to do is I want to simplify this matrix. However, this is still a bit too much to write down, so we shorten this even further by leaving out the variables and only writing down these numbers and those numbers. Then we try to use some commands to get this matrix here on the left to look like an identity matrix. And we're going to do this in 3 steps. So this is what we want to get, because then once we have this here on the right would be our solution. So we have 3 possible steps we can take. First off, we can switch to rows. Second, we can multiply or divide any row with any real number except for 0. And we can add or subtract a row to or from another row. And if we take the second and the third together, means we can add or subtract the multiple of one row from or to another row. This is used to first actually get our matrix on the left to look like an upper triangular matrix. Then get ones for all diagonal elements, and then make it look like a diagonal matrix, which is actually the identity matrix. If we apply it in this fashion, we have 3 possibilities for the outcome. Classically, on the left we get a full identity matrix. If the matrix actually has more equations than variables, we have a full identity matrix on top, and the rows below are only zeros. And on the right side of them are also only zeros. So for example, something like this. We have a full identity matrix here. Below here, we have one row where on the left and the right, there's only zeros. This means we have exactly one solution, and the solution is given here on the right of the identity matrix. An alternative would be if we have no solution. This can happen in different situations, but it's always determined by the fact that on the left, here on the matrix, we have one row with only zeros, and on the right side, this corresponding row, we have something which is not 0. So this would read as 0 is equal to 3. As 0 is not equal to 3, this is not possible, so this means we do not have a solution to our system of equations. So either one solution, no solution, or, and that's the third case, we can have infinitely many solutions. In this situation, we cannot get a perfect identity matrix on the left side. For example, something like this. We have some rows with zeros, so no problem there, but I cannot establish a full identity matrix here. So this is always an indicator of infinitely many solutions. And well, once you know that there are infinitely many solutions, you can also discuss how they actually look like. For this, we decide on one variable. In this case, as we have one equation, but 2 variables, we have to select one variable. You always can go with how many variables do I have, how many equations do I have, and then go variables minus equations. That's how many variables you have to determine. Here I determine it to be the x2, and then I write all the other variables in relation to those fixed variables. So here I'm writing everything in relation to the x2. Well, everything means only the x1. So if I write down this equation, you can say, well, this is the equation. I can write it as x1 is equal to minus x2 plus 5. That's one thing. And I also know that, well, obviously x2 is equal to x2. So this then is my solution. However, I again can write this in a vector notation. So this solution would be here, if I factor out the x2, this vector plus this vector. This is more or less description of a line. That's more from analytic geometry, but this is nothing else than a line in 2 dimensions. That's here the absolute, where this line starts. This is the direction where it's going, or the slope. So here my solution is actually an infinite amount of possible outcomes, which all are arrayed on a specific line. And that's actually what can always be said. If we have infinitely many solutions, either we have them all on a line, on a plane, on a hyperplane, whatever, but we can always write this down in this fashion. With those here, the variables we have to set because we're missing them here in this part. Well, that's basically all there is on the Gauss algorithm. It's the 3 or 4 steps I mentioned earlier, and then you can get, if you follow the procedure trying to establish an identity matrix, either a full identity matrix, the rest is 0, then you have one solution, you get some kind of problem with one side being 0, the other not. Then in this case you have no solution, or if you cannot establish a full identity matrix, you have infinitely many solutions, whereas this would be a way how to express them. Well, as I said, that's all there is, so I hope you enjoyed it. I'll say goodbye and see you next time.